blemish the surface if it's on a core. Just a marginal blemish. You're talking about 2-3 millimeters depth in the middle, and then it'll be a perfect surface. But that's something we can live with, okay, rather than seeing a big core being taken from it. Okay? So that's what the test was developed for. Oh, I should have remembered that I have all these drawings there. But I like to give you the visualization, and then you can see the difference. So that's the disc, the metal disc on the left side, and you glue that on the surface, and you probably leave it overnight, let it settle, and then see the thread on top of that disc. So the machine attach itself to that, and then you can pull it off. Okay? See the way there are two lines there? So if you do that, you'll get the strength of the material. But if you want to get deeper strength or deeper bond, you then cut the edge using a core, and then you pull off. So then you get the failure line to be a bit more deeper. And that's the same technique they use for debonding part. Okay? So I did say this was developed in the 80s. Since the 80s, there's a lot of tests available now on the same topic. Okay? And interestingly, most of them are cheaper. So I think this instrument is probably £4,000 worth to buy from some of the companies. But if you look in Google, you can actually get something as close to £1,000. And that's a difference. And that's what I would expect all of these durability systems to evolve. Unless it evolves, it's a dead end. Okay. Happy enough? Okay. So let's move on to sensor systems. Once again, I'm only introducing sensors that I'm familiar with or I've worked with. But sensors is an area to watch out because it's evolving every second. There are new sensors coming out in the market. There are new technology coming out in the market. Monitoring is cheaper now than ever before, so I'm sure in the future your mobile phones will be capable of monitoring yourself entirely and anything around you. You're laughing, but it's not too far from it. I'm being constantly monitored and GPS tracked. So first of all, for those who are in the business of selling, you have to be able to sell the sensor technology to the client. That's the most critical part, because if the client doesn't agree, you can't really, it doesn't fly. So where do you think sensors will become beneficial for you? All sensors does, no matter what it measures, it gives you a measure of performance, whether that's performance in terms of strength, so it's stress and strain sensors, whether it's performance in terms of temperature, if you're looking at a thermal gradient factor, performance in terms of moisture or chlorides, pH, anything. That's all it does. It'll measure one thing that you tell it to measure. It'll do that measurement. It'll give you information as frequent as you want. Some sensors can give you measurement every minute. You wish they don't do that. So all it can do is it can tell you the value at the start, and it can tell you whether the value is dropping or increasing. It give you absolute values, obviously. So it is entirely up to you to decide whether that value is good or bad. And even before you put the sensor in, you need to have a strong sense that what the value coming out of it tells. If you cannot tell that sensor's value being this is good or bad, that money is wasted. Okay. So where we use sensors is to tell whether the performance is acceptable or not. So in some cases the performance might be the client doesn't want the water out of the swimming pool to leak out. Okay, swimming pools are a good example. So if you attach sensor on the outside of the swimming pool and if you see the moisture values increasing, you know where the source of the moisture is and you know what's happening. And then you can take a remedial measure, which is basically emptying the swimming pool. Can't really do much. And the same for structures. If you see that the strain that the steel is taking is increasing, there is something to worry about. Okay, it's either that the load that the structure is taking is increasing, or that the structure is rediverting stress from somewhere which has failed to the point that you're looking. Okay. You can do that intermittently, or you can do that continuously. Continuous strain censoring is extremely expensive because you will need to be investing time and money to go and collect the data, process the data, take the report. And also remember, if you do that, you become liable. You are monitoring something and you're meant to be telling them that's going. Okay. So intermittent sensors are a person you send to site as a sensor. You're sending a person to site to look at everything, to say there's nothing happening in the structure. They're visually examining the structure, and that's sensing. The person is sensing and conveying the message. The other is you put a sensor on the reinforcing steel and you let a known vehicle pass through, a 40 ton or 80 ton or whatever. Put a known vehicle pass through and you know the behavior should be such. Okay. There's most complicated mathematical models or analytical MATLAB, or what is it called, the new things on structural engineering, Abacus, or any of those softwares that are available, so it can tell you the strain and stress that a steel bar will take. So you have a reference value from your design calculation, and you go and expose a rebar in your concrete. Maybe corrosion has done the job for you. You can clean it up and you can put the sensor there, let a known vehicle go through, and if the strain on the rebar is nothing, which is highly likely the case, then you know that this is okay, 40 ton is easy. You clean it up, you patch it and say, test it at that point, 40 ton is fine. You prefer this to be tested in a few years' time. Intermittent sensors, intermittent sensing. Okay. So the nature of sensing will clearly depend on the importance of the structure and the money that the client has to spend on it. So with that, you can estimate a service life. Okay, so if the strain values are constantly increasing, then you know at a certain stage you will reach its capacity. Therefore, that's your service life reached. Or if you're happy for the structure to slowly deteriorate, you can extend the service life. But it has reached a certain performance, and that's what these graphs represent. So structure 1, which is represented by the top curve, means it's never reached its minimum performance level. It's always above that. It's a good structure. You might invest significantly in making the structure, but that's okay. It's your choice. Structure 3 is very typical. It starts great. No maintenance means no maintenance means you start to deteriorate consistently. You do a repair. That's what the spike is. Like that, you go in different cycles. So every cycle is costly. It's intervention, so it's very nuisance for the public. Number 2 is structures that never perform totally. So at some stage it has completely gone out of the window. So in reality, we have all of these structures in our asset. So you'll need to decide which one you want to track. Okay. So we looked at 2 kinds of sensors, and electrical resistors is what I prefer. I'll explain why later on, and you will see why. Fiber optic sensors, because that's where the money was. In UK research, we go after where the money is. So fiber optic sensors is something cool to talk about. So we did a lot of work on that. But beyond that, we also had the intention that if fiber optic sensors can be developed, it is expensive to monitor using fiber optic sensors. But if the next level comes up, which is called distributed sensing, fiber optic sensing is the cheapest and the most stable sensors you can use. We haven't reached there yet, but I don't think we're too far from it. So most of the sensors are single lens sensors. You have a sensor which monitors something, sends a signal back. It's called a single lens sensor. The reason why we were looking at fiber optics is that you can have a large fiber optic cable which has different sensing points alongside it, because it's a wavelength of light coming back. We can even tell where the light is coming back from depending on the delay it comes back. Okay. And that advantage cannot be done on a cable based sensor, and that's why we were keen on fiber optic sensor. Electrical resistance sensors was pioneered by a person called John MacArthur. He's from Hereward University in Edinburgh. He still is in Hereward University in Edinburgh for another 2 weeks. He's retiring. So I worked with him during my PhD and afterwards, and I continue to work with him because those sensors I think is very useful and very cheap. So where are we going with this? Okay. So for carbonation, the existing methods are, you just split open, spray phenolphthalein, great. Please don't smell phenolphthalein. It's a very nice smelling chemical, but you shouldn't smell it. But along with phenolphthalein, there's also other indicators that you can buy. It can give you a range of pH. The pH indicators, they're commercially available. You can buy all of them. Just read the small label, because most of them can be cancerogenic. So just read the small label. So that means if you have the luxury to spray it in different surfaces or different laboratory-based system, you can spray with different chemical and get a grade of the pH, not just one pH. The phenolphthalein gives you only one pH change. I think 11 or 9.5. Forgot now. Is it 11? Phenolphthalein. Okay. Okay. So I think the value comes up later. It converts itself. So the pH indicator means when you spray it on a surface, it changes its color when the pH threshold is reached. So for phenolphthalein, it could be 9.5. That means that area has a pH lower than 9.5, which is very low, by the way. Anything below 11, you can start to expect problems. But some of the concretes that we now work with has a starting pH of 11. But there's no threshold in that case. The chloride threshold that you asked earlier means it's questionable for that. So the existing methods for carbonation are X-ray diffraction of concrete dust. It captures the calcium carbonate part of it. Thermogravimetric analysis, sounding great, basically burn the life out of the powder, and you see the mass loss as you burn up to 1,000 odd degrees. Every mineral burn at a different temperature, so you can see when you plot it back, you can see the weight of the concrete dust or cement paste that you started, and then you will see as the temperature goes up, you will see the drop in weight. It never gains, but so each drop quantifies how much of mineral has been burned at that temperature. Each mineral burns at a given temperature. So it's a very small amount of powder that you use, so it's not really a big test, but it's not a complicated test either. Chemical analysis of concrete dust, again you're tracing for calcium carbonate, I think, or pH, you can do that. Petrography does the same. I think it looks at density, I'm not yet sure. But these are very, very destructive in nature. Not so extreme for phenolphthalein. If you happen to take a core or drill for chloride, you can spray the reagent with phenolphthalein as well. For site practice, I would say have silver nitrate in a bottle and phenolphthalein in a bottle, because it gives you confirmation that I'm not looking at the major troublemakers, that I'm looking at something else. So what we wanted to do with the carbonation was to see if fiber optic sensors can tell us the pH value. Okay. Along with the distributed sensing, that was our drive to go towards fiber optics. The fiber optics can tolerate higher temperature and vibrations and anything else. So, but the only thing is, the technology that's available then with fiber optics is that you can create, you'll see in a minute how we do sensing with fiber optics, but essentially if you take it for now, that you have a long fiber optic cable and you put a chemical every set distance. If the chemical can change color due to pH, it's basically a pH indicator gel. That means fiber optic can tell us what is the color of that point. It's very simple in that sense. So it's a gel that changes its color. The only thing is it's not a reversible reaction. If it changes its color, done, it has changed. But we wanted a value out of it. And that means we needed to create a color stable gel which has a grading of colors. So pH 11 is, let's say, yellow, pH 10 is orange, pH 10 is more purple, like that. We wanted a spectrum. Nanotechnology is the answer. We didn't have the answer then, so we're starting to use what's called gold nanoparticles in it. Okay, and that seems to have helped. I'm not sure where we've reached in this at the moment, because this work was done by Professor Bashir and a few other students of his. So that's how it looks like. So that stainless steel end has a fiber optic cable inside, and each fiber optic cable is, so this, in improving the technology, we were using the end of the cable, end of the fiber optic cable. So that's what this is, and the gel was sitting at the end. That was enough for us to say the technology will work or not. Okay. Ideally, what I would have liked to see is a long cable with all of these spots sitting, but that's far from it. And these are the different, so the cable comes back to a light source and a spectrophotometer which analyzes the light to say it's of this wavelength. That's what the results. These are the two gels that we were using at that point. You can see the size of the sensor. It is extremely small. 20p coin is less than your new 1 rupee coin. Okay. So it's a very small thing. Just like anything else, we make the sensor, we put it in the concrete very carefully. It's like a clinical precision concreting. And that's what we got. We were able to get the pH values against time. Bar, there was one problem. It wasn't reversible though. Once it changed, that's it. You can only pick up anything higher or lower. So in this case, its pH was increasing during casting. So this is poured concrete, and then it's increasing its pH, so it's changing. And then it remains. It doesn't come down. Extremely expensive. Sensors are not really expensive. Fiber optic cables are not expensive. But the measurement head will cost around £10,000. The biggest, sorry, I'm wrong. You can buy a ready-to-go monitoring system from the Slovenians. There's Slovenian universities have these technology developed. But the sensor head was developed at Queen's. So the measurement head is the same. It's a spectrophotometer, it's a light, it's a source. It gives you an interface. And that's where the money will be lost. It's nearly £10,000. But the sensor heads you can create, you do need very different skill set. You do need a person who can splice the sensor. Splicing is perfect cutting of the sensor. And joining of the two sensors. So there's a splicer available. It might be cheaper, much cheaper in India. I think we secured it from India. So there are two kinds of fiber optics. The cheap fiber optics that's all over the show, and there is extremely expensive glass fiber optics, glass based. We needed the glass for measurement, but we didn't need to spend cabling. So that's where the splicing comes in. You take the plastic cable, you cut it, and you put the glass one in, fuse them together. It's very small, so it's a precision work. And then you can put a sensor head on top of it. So you need a steady hand, person with a steady hand, capability of handling photonics, and you need a chemist or somebody who can handle nanotechnology. Because most of the guys are using gold nanoparticles or color particles for creating the sol gels and everything else. So, yeah. It was a joint project with City University London, and they were the physics experts. They had an instrumentation expert, because this is beyond our capability. And we were doing the concrete and the sol gel support from our labs. Yeah, it's pH measurements. Yeah. So you get the wavelength, you can convert that into pH. You do the trials beforehand on which wavelength was what. So you get pH as an output. No, no, not yet. Not yet. I think it's a bit far from that. The sensor heads are available, the instrumentation is available through the Slovenians. We now buy it, we don't make it anymore from them. But they're specializing on strain and stress sensing. Yeah, and pressure. So if you're looking for that, you can buy the sensor head and the sensors. But any of the durability work, the sensing part of it needs further work. It's not ready commercially. It's not stable, to be honest. Because one of our biggest problems was the sol gel keeps cracking all the time. If they crack and be non-stable, then we can't use it. It took us months to get it to not to crack. So it's far from the market, unfortunately.
You said the change the lights.
Yeah. So I think this is the minimum kit. If you're able to interpret the data from a